everyone, in this video we're going to work on rationalizing denominators. So there's this rule, and it's a bit dated at this point, but it still gets us to practice some really good skills. And the rule is that you don't want radicals in the bottom of fractions. So truthfully, the skill that we want to build up is being able to eliminate radicals from the top of fractions for calculus. But this is just kind of a traditional thing to write all answers without radicals in the denominator. And in 142, it'll help us all simplify things the same way. And like I said, in calculus, it'll help us rationalize numerators. So looking at this first one, this is actually a little bit of review. Remember to always just check and see if there's an easy solution before we worry about any tricks that help us get rid of radicals. In this case, the easy solution is to split the radical. You can always split radicals over multiplication or division. And once you've split the radical, hopefully we notice that 81 is in fact a perfect square. So we can take the square root of 81 and get 9. And that has now been rationalized. The denominator doesn't contain any radicals, so we are done. You should also check and make sure that you can't extract roots from the numerator if you're trying to fully simplify something. But root 31, I think we're stuck there, so we can call that one good. Okay, next example is another one that's a bit of review. In this case, it actually helps to combine the radicals. So we can take 54 over 6, and 54 over 6 is 9, so we actually end up with root 9, which is just plain old 3. So sometimes you can do this without a whole lot of work if you just pay attention to what the numbers inside the roots are. Do check for that. It'll make your life a little bit easier. But the trick to actually eliminate the radical when you can't do one of those two things isn't so very bad either. So if you ever miss one of those, it shouldn't be the end of the world. The idea here is we would like to eliminate the root 5 from the bottom of this fraction. And to eliminate a square root, we know we need a perfect square. So we're trying to create a perfect square in the bottom of this fraction. A lot of times the first thing that people think of is just squaring the fraction. Why can't we just square the whole thing? And you actually have the right thought. The problem is that when we're simplifying something, which is what we're doing, we don't want to change its value. 5 over the square root of 5, that's a number. You could plug it into a calculator to get a decimal approximation if you wanted to. If you square that number, it does not have the same value. It is now an entirely different number, and that does not count as simplified. That's actually changing the number. So if we think about what squaring means, it means multiply by itself, and we do have a simplification trick that allows us to multiply something by itself as long as we do it top and bottom. So one of our really good simplification tricks is multiplying by 1. We use it to get common denominators, and we can use it to rationalize denominators as well. So when I do this, in the top I get 5 root 5, and there's not really anything to be done with that, so I'll just leave it. But in the bottom I get the square root of 25, and the square root of 25 is in fact 5. So we did successfully square the square root, and we end up with just the number that we started with under the square root. Sometimes these fractions will reduce, and this is one of those sometimes. And in this case, we actually end up with just the square root of 5. Again, always check that final answer to see if you can extract any roots, but I think we're great with root 5. We'll just move on from there. Okay, root 5 over root 11. This one has a square root top and bottom, but that doesn't really change our process much. Our goal here is to get the root out of the denominator. So if we want to eliminate a square root, we need to create a perfect square. So we will multiply root 11 by itself. To maintain the value of root 5 over root 11, we also multiply the top. So we are multiplying by 1, which is always allowed. Okay, so when we do this, we get root 5 times root 11 on the top, which we can combine into root 55. On the bottom, we get root 11 times root 11, which is root 121. You are welcome to skip the step where I write out that root 21 and just skip to 11 if you're seeing that clearly. But I'm going to be very careful about it just to make sure that we're really seeing that what we're doing is building the square root of a perfect square. And that just leaves us with root 55 over 11. Okay. Next, 4 times the square root of 3/17. And that is a 4 times, not a fourth root. So that 4 will just hang out in front. I just wanted to point that out because sometimes you'll see that. I am actually going to go ahead and split the root up this time and say, well, root 17 is not a perfect square the way the very first example had a perfect square. But I can now see that I need to multiply top and bottom by root 17. And I'm going to go ahead and put that 4 in the top of the fraction. So I get 4 times the square root of 3 times 17, which is 51. And then on the bottom, I have the square root of 17 squared, and you can put that square under the root or outside the root, either way. I don't actually know 17 squared off the top of my head, so I'm just going to leave it written like that and say, okay, well, whatever 17 squared is, when I take the square root of that, I should just get back to 17. So there's my simplified answer. Next one, let's get some variables in the mix. This actually jumps to something really scary looking. I notice I didn't actually put very many with variables, but they don't really make it much trickier, although this one is a little tricky. I have x over the square root of 3x cubed y. You could go straight to rationalizing, or you could actually start, if you wanted to, by extracting an x squared out of that. I think I'm actually going to go that way, but you would be fine to go ahead and start multiplying top and bottom right away. You'll just have to then simplify a little bit at the end. So one way or another, you're going to do the simplification. It's just a matter of when you do it. So what I'm thinking is I could split an x squared out of that. So I'll have the square root of x squared times the square root of 3, and then a single x and a y will be left. So that breaks down into x times the square root of 3xy. So let me just rewrite that up here, clean up my mess a little bit. So I do get to cancel an x out right from the beginning. Again, if you did this in a different order, you just end up canceling that x at the end instead of at the beginning. Now I'm going to go ahead and say I need to eliminate that square root. So I need to multiply by the exact same square root, top and bottom. I'll get a root 3xy over the square root of 3xy squared, which will just be a 3xy. So you don't have a lot that get terribly messy, but there's a couple in there just to make sure it doesn't throw you off when it looks a little uglier. The truth is that it's the exact same process, so don't let it throw you off when it starts to look a little messy with variables. Okay, just a couple more of these. This one, again, looks a little messier, but the goal is the same. The goal is to not have radicals in the denominator, so I'm not worried about the root 2 in the top at all. But I am a little worried about the root 2 in the bottom. I would like to eliminate that. To do that, I need to multiply by a square root of 2. So the 3 doesn't really affect my goal here at all. It can stay in the denominator. I'm fine with that. I just don't want a square root. So I will multiply the square root of 2 in the top, and I'll do that by distributing. So I get the square root of 2 squared, which is 2, and then minus a 5 root 2. On the bottom, I get 3 times the square root of 2 squared, which again is just 2. So it's 2 minus 5 root 2 over 6. And that's a great answer. I just don't want radicals in the bottom, and I want to extract roots if possible. There's nothing to extract from 2, so I think I'm set. All right, 2 more here. I don't want to spend a ton of time on higher roots, but I do want to build up this idea a little bit. The idea is that to get rid of a square root, we build up a perfect square. If we want to get rid of a fourth root, we need to build up a perfect fourth power. So in this case, I have 6 over the fourth root of 3, which means that to make it a perfect fourth power, I actually have to multiply by the fourth root of 3 cubed. And again, you can put that cubed under the root, or you can put it outside the root. It doesn't really matter. It means the same thing. So whichever way makes more sense when you're thinking about this process is fine with me. So on the top, I'll get 6 times the fourth root of 27. And in the bottom, what I'll get is, I'll write it out again for this one, the 4th root of 3 to the 4th, or the 4th root of 81. And there I've built up what I'm hoping to build up. So again, avoid the temptation to say, well, I'll just raise the whole fraction to the 4th power, because that changes the value of the fraction. We want to have the same number with a different appearance, and this should do it for us. So 6 times the 4th root of 27 all over the 4th root of 3 to the 4th, which is just 3. Okay, just one more time with that to make sure that we're feeling okay about it. Let's see. I have cube roots this time. So to get rid of cube roots, you'll need to build up a perfect cube. So I need to multiply by the cube root of 2 squared. And again, however you want to think about that, if you like the square outside the root, you can do that as well. And what will happen is I'll get the cube root of 10 times 4. I'm just going to go ahead and simplify that, which is 40. And then on the bottom, I get 4 times the cube root of 2 cubed. So I have a 4 times 2 is 8. You can even write that out if you want. That's not such a big number. And the cube root of 8 is 2. So I have 4 times 2 on the bottom, which is 8. On the top, I have the cube root of 40. And remember, I said always check to see if you can simplify. I actually can simplify that, which maybe means if I had mushed fractions together, that would have helped as well. That's 8 times 5, and 8 is a perfect cube. So I can actually make this the cube root of 8 times the cube root of 5, which is 2 times the cube root of 5 all over 8, which is cube root of 5, and then when I cancel that 2 out, I'll just get a 4 in the denominator. Okay, so they can get a little scary looking, but remember, the goal here is to use the inverse operation. If we want to get rid of a square root, we need a perfect square. For a cube root, we need a perfect cube, and for a 4th root, we need a perfect 4th power.